In section 9.5, we're going to learn about the kinetic-molecular theory of gases, and we're going to talk about how this theory can be used to explain the gas laws that we've already seen. So, kinetic-molecular theory. In this theory, gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or the walls of a container. The molecules composing the gas are negligibly small compared to the distances between them. The pressure exerted by a gas in a container results from collisions between the gas molecules in the container walls. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic. They do not involve the loss of energy. The average kinetic energy of the gas molecules is proportional to the temperature in Kelvin. So this theory goes a little bit further to explain what we saw with the ideal gas law, but you notice that we're still only allowing for straight lines that do not change, so they can't have any curved trajectories. The molecules have to be relatively small, so we still need a dilute gas solution with higher temperatures and lower pressures. And most importantly, we're still not allowing for any sort of forces between the gases themselves or with anything else around them, which we know to definitely not be true. And this would actually mean that collisions between the gases aren't going to be perfectly elastic. But still, it works pretty well. So if we look at Amanton's law, we know that the pressure and the temperature are directly proportional. If the temperature is increased, the average speed and kinetic energy of the gas molecules would increase. And we know that kinetic energy is equal to 1/2 times the mass times the volume squared. So this is consistent because if the volume is held constant, the increased speed of the gas molecules result in more frequent and more forceful collisions with the walls of the container, and that's going to increase the pressure. So if every molecule has a higher kinetic energy, it's going to exert more force on the walls of the container when it strikes it. With Charles' law, we know that volume and temperature have a direct relationship. So increasing the temperature increases the kinetic energy of the gas molecules. Increasing the volume of the gas increases the distance gas molecules travel between collisions while increasing the surface area of the container. Pressure is held constant when the number of collisions decreases and the kinetic energy of the molecule increases. So if we're making the container larger and larger, then we're going to need more kinetic energy so that every one of the collisions that still happens adds up to the same amount of pressure if we want the pressure to be constant in this scenario. And that is consistent with our first equation here. So Boyle's law, we know that pressure and volume have an indirect relationship. So in this scenario, when the volume of gas increases, the collisions with the container decrease. This leads to a lower pressure. When the volume of the gas decreases, the collisions with the container increases, and this leads to a higher pressure, which is pretty self-explanatory that those two would be opposed to one another in this scenario. Avogadro's law. So we know that there is a direct relationship between volume and the number of moles. So when more molecules are added, the container volume must increase in order to maintain the same number of collisions with the container. More molecules, they're going to have more collisions. We're going to need to spread that over a larger surface area on the inside in order to maintain the same average number of collisions per unit of the container's surface area. When molecules are removed, the container volume must decrease in order to maintain the same number of collisions with the container. And Dalton's law. The molecules of one gas in a mixture bombard the container walls with the same frequency whether other gases are present or not. And we know this to be true because we set up in KMT theory that they don't interact with each other, right? So if the gases don't interact with each other, they don't really care whether those other gases are the same as them or not, right? They're just going to continue to do what they would have done regardless of if there's any other gases present. So here we can picture this. So if we have our baseline here and we add heat, each one of the molecules starts moving a little faster with more kinetic energy, and it's able to increase the pressure. It hits the walls of the container harder. Again, if we have our baseline and we decrease the volume, now all of these molecules are pushed together and they're going to have a shorter path before they get to their next collision. And so that's going to make collisions more frequent and the pressure rises. Here we have our baseline, and if we increase the number of gas, the amount of gas in there, again, now there's more atoms or gas molecules to hit the containers, and the pressure rises and the piston moves up. So the Maxwell-Boltzmann distribution is an attempt to use statistics to describe all of the moving gas atoms and molecules. And it's similar to what we saw with the work of Schrödinger and Maxwell before, where we're going to use statistics in order to describe a situation that we can't really calculate perfectly each individual atom, but we can do it when we have like a whole bulk, and we can talk about what in average they're doing, just like we did with electrons and orbitals. So here, gases are comprised of many moving atoms and molecules traveling at different velocities, leading to a varied kinetic energies. Modeling the velocities and positions of each atom is impractical, impossible, and unnecessary. The Maxwell-Boltzmann distribution describes the statistical distribution of velocities within a gas sample, and it's a type of probability distribution function, which is the same as what we saw for psi squared when we were talking about molecular orbital theory. So here we have this speed of each one of the molecules, and then we have the number of molecules that are doing it. And you can see that there's most of the molecules are right around the same speed, but we're going to have at least a couple that are moving quite a bit faster and a few that are hardly moving at all, but the bulk of them are going to be the same. And we're going to talk about what this URMS and UP is in just a second here. So KMT uses a statistical parameter called the root mean square velocity, URMS, to describe the average velocity of all the molecules in the gas. And the way that we are going to calculate URMS is as the square root of each individual velocity squared, all the way till we've added up all of them, and then we're going to divide it by the number of them, and we're going to take the square root of that. This should seem a little familiar to you. This is very similar to the standard deviation equation that we've used before, and is not very dissimilar from like the Pythagorean theorem or the distance equation for multiple dimensions. You probably have seen this in mathematics before. And the effect that we get is that squaring each of the velocities ensures that you only sum positive values. So these are vectors. They could be negative, right? Depending on the direction of the molecule. But if we square them all, we get all positives. We add them together, and then we take the square root, and we get something that's kind of like an average. It's not exactly an average because obviously the square root does not distribute across a sum, but it gives you a value that's kind of close to that. It kind of has a similar meaning. URMS is substituted for V to calculate the average kinetic energy of the gas. So we can plug it in there, and we can get the average kinetic energy of that gas, and that's kind of how I was saying it kind of behaves like an average. When M is expressed in kilograms per mole, the kinetic energy will have units of joules per mole. The kinetic energy of an ideal gas is also equal to 3/2 RT. So we know this from using calculus, but it's just in general a fact. And if we set them equal to one another, we will get a equation that we can use for the average velocity, the RMS velocity for an ideal gas. If the temperature of a gas increases, more molecules have higher speeds and fewer molecules have lower speeds. The distribution shifts towards the right. If the temperature decreases, more molecules have lower speeds and fewer molecules have higher speeds, and the distribution shifts towards the left. So let's see what that looks like. So we can see as the temperature increases, we get more and more molecules that are moving quite rapidly out here, and the whole thing starts to kind of flatten out, and we get just a wider distribution in general. Whereas when it's a little bit colder, you see that there is a nicer, tighter distribution of RMS speeds. Mass and velocity distribution. We've seen that the kinetic energy of an ideal gas is dependent only on the temperature. This means that when the temperature is held constant, the mass of the molecule is inversely proportional to the velocity. So if we go back here and we want to go ahead and solve for M, we will get this value here, provided that we hold the temperature constant. Here's an example of the velocity distributions based on mass for various different noble gases at the same temperature. So KMT also works for effusion. The rate of effusion is proportional to the RMS velocity. This is consistent with Graham's law. So if we plug in our RMS velocity and we plug in our equations for that, and we simplify by canceling these numerators, we will get back to Graham's law.